Right this very moment, as you sit watching this video, the cosmos is unfolding in ways that defy logic, challenge our understanding, and ignite pure wonder. Imagine a place where stars explode silently in the void, black holes dance in gravitational embraces, and entire galaxies vanish without a trace, all while we go about our daily lives utterly unaware. The universe isn't just vast, it's alive with mysteries, each one more bizarre than the last. And here's the thing, you don't need a telescope to witness them. These aren't relics of the distant past or far-off futures. They're happening now in real time in the infinite theater of space. Think about that for a second. Somewhere out there, a neutron star is spinning so fast it could slice through dimensions. A cloud of alcohol floats in deep space, large enough to fill 1 trillion cocktails. Planets rain molten glass sideways, and invisible forces tug at the fabric of reality itself. These aren't sci-fi fantasies, they're real, documented phenomena, and they're unfolding as we speak. The universe doesn't just have secrets, it is one, a riddle wrapped in enigmas, and today, we're pulling back the curtain on 25 of the most mind-bending cosmic events happening right under our noses, or rather, right above our heads. So why does this matter? Because every one of these bizarre events is a clue, a piece of the grand puzzle that is existence. They challenge what we think we know, push the boundaries of science, and remind us that the universe is far stranger, far more magnificent than we could ever imagine. And the best part, you're about to embark on a journey through them all. From the eerie whispers of rogue planets to the cosmic fireworks of colliding neutron stars, this isn't just a list, it's an expedition into the unknown. Buckle up, the cosmos is waiting, and it's weirder than you've ever dreamed. Right now, in the depths of space, invisible waves of energy are screaming across the cosmos, brief, violent bursts of radio waves so powerful they outshine entire galaxies for mere milliseconds. These are fast radio bursts, or FRB, and they're one of the universe's most tantalizing puzzles. Imagine a cosmic lighthouse flickering just once, vanishing before you can even pinpoint its location. That's what astronomers face when tracking these signals, a fleeting blip from billions of light years away, packed with more energy than our sun emits in 80 years. And here's the kicker, no one knows what's causing them. Some FRBs repeat at random intervals, while others are one-off explosions, as if the universe is playing an erratic game of Morse code. Theories range from the apocalyptic colliding neutron stars, magnetars throwing tantrums, to the downright speculative, alien megastructures, interstellar beacons, even echoes of parallel universes. One leading candidate involves hypermagnetized neutron stars called magnetars, whose crusts can snap under unimaginable pressure, releasing energy quakes that ripple across space-time. But even that doesn't explain the bursts with bizarre patterns, like the infamous FRB 121102, which pulses every 157 days like clockwork. Then there's the creepy factor. In 2020, astronomers detected an FRB originating from our own galaxy, the first time we've caught one so close. Its source, a magnetar just 30,000 light-years away, confirming these things aren't just distant anomalies, they're happening in our cosmic backyard. Whether natural or otherwise, FRBs remind us that the universe is far from silent. It's shouting in a language we're only beginning to decipher, and every burst is another piece of the puzzle waiting to crack open our understanding of reality itself. While we're still puzzling over fast radio bursts, another cosmic mystery is pulling entire galaxy clusters across the universe like leaves caught in some unseen river. Astronomers call it the dark flow, a strange phenomenon where hundreds of galaxy clusters are racing toward the same distant point at mind-boggling speeds of nearly 2 million miles per hour. And here's what makes it truly bizarre. This movement defies everything we know about how the universe expands. According to our current understanding, the Big Bang should have sent matter flying outward in all directions evenly, like an inflating balloon. Gravity from dark matter then sculpted this expansion, creating the cosmic web we see today. But the dark flow breaks all the rules. These galaxies aren't just moving apart as space expands. They're being pulled as a group towards something massive beyond the observable universe. Imagine dropping marbles onto a trampoline and watching them all roll toward the same hidden weight at the edge. That's essentially what's happening on a galactic scale. The leading theory suggests this could be the gravitational tug of structures so enormous they lie beyond our cosmic horizon. Perhaps other superclusters or regions of space so dense they warp reality itself. Some researchers speculate it might even be evidence of other universes brushing against ours in the multiverse, their gravity leaking through like footsteps in the apartment above. But here's the twist: we'll likely never see what's causing it. The observable universe has a hard limit about 93 billion light-years across, and whatever's pulling these galaxies lies outside it. What makes the dark flow especially unsettling is how it challenges two pillars of modern cosmology: that the universe is mostly uniform at large scales, and that dark energy drives its expansion evenly in all directions. If galaxy clusters are being herded by some unseen force, it means there are structures or influences out there we've never accounted for, a cosmic blueprint missing entire chapters. As one astronomer put it, it's like realizing the ocean you've been mapping has currents flowing toward a continent that doesn't appear on any of your charts. The implications are staggering. If confirmed, the dark flow suggests our universe isn't just stranger than we imagined. It's stranger than we can imagine, with entire realms of physics operating beyond our perception. And right now, as you watch this, hundreds of thousands of galaxies are caught in this mysterious current, carrying them towards some unfathomable destination we may never comprehend. Hovering like a ghost in the afterglow of creation itself, there's a chilling anomaly in the cosmic microwave background, a sprawling, cold spot, so vast it could swallow 10,000 Milky Ways. This isn't just a blank patch in the sky, it's a cosmic bruise, a region significantly cooler than its surroundings, defying everything we know about the uniform haze left by the Big Bang. Picture the universe's baby photo, that static-like glow seen in old TVs, but with a mysterious shadow stretching across one corner. And this shadow isn't just a glitch, it's a full-blown cosmic mystery, one that has physicists debating parallel universes, cosmic defects, and even errors in our fundamental understanding of reality. What makes this cold spot so unsettling is its sheer scale and stubborn refusal to fit conventional explanations. Normally, tiny temperature fluctuations in the cosmic microwave background are just cosmic wrinkles, evidence of density variations in the early universe. But this spot, it's 7 times colder than standard models predict, spanning nearly 2 billion light-years. At first, astronomers thought it might be a supervoid, an enormous emptiness where matter is unusually sparse, causing light passing through to lose energy and appear cooler, a phenomenon called the integrated Sachs-Wolf effect. But when they mapped the region, they found it wasn't empty enough to explain the temperature drop. The numbers simply didn't add up. This is where things get wild. One radical theory suggests the cold spot could be a cosmic birthmark, evidence of a collision with another universe in the multiverse. Imagine 2 soap bubbles brushing against each other. Their meeting point would leave a disturbance in the fabric of each. If our universe bumped into another during its early expansion, the energy drain from that encounter might have left behind this eerie cold patch. Another idea points to topological defects, exotic relics from the universe's infancy, like cracks in space-time formed when fundamental forces split apart during the Big Bang. These cosmic scars, known as textures, could warp the surrounding space, leaving behind cold imprints. Yet the most unsettling possibility is that there's no exotic explanation at all, that the cold spot is just a statistical fluke, a 1 in a million random variation. If true, it would mean our models of the universe are missing something profound, and we've been overestimating how well we understand the cosmos. Either way, this frigid enigma serves as a humbling reminder. The universe's baby picture has shadows we still can't explain, and some of them might be windows into realms beyond our own. Right now, as you watch this, that cold spot is still there, hanging in the void, a silent challenge to everything we think we know. Out beyond the frosty realm of Neptune, something massive is stirring the cosmic pot, an unseen force tugging at the orbits of distant icy bodies with gravitational fingers. Astronomers call it Planet 9, a hypothetical world up to 10 times the mass of Earth, lurking in the solar system's dark frontier. And if it's real, it's rewriting the rulebook for how planetary systems form. The clues started with a peculiar pattern, a cluster of extreme trans-Neptunian objects, icy relics from the solar system's infancy, all swinging around the Sun on eerily similar tilted orbits. Statistically, that shouldn't happen by chance. It's as if an invisible shepherd is herding them. The hunt for Planet 9 reads like a cosmic detective story. Unlike other planets, we can't spot it by its reflected sunlight. At its estimated distance, the Sun would appear as little more than a bright star, offering barely any illumination. Current models suggest it could orbit up to 600 times farther from the Sun than Earth does, taking anywhere from 10,000 to 20,000 years to complete a single trip around our star. That's an orbit so vast light itself would take weeks to traverse it. Even more perplexing, its orbit is likely highly elliptical, meaning it spends most of its time drifting through the outer darkness, only occasionally swinging closer to the inner solar system. Theories about its origins are just as wild. Some suggest it's a rogue planet captured by the Sun's gravity during the solar system's chaotic youth. Others propose it formed closer in but was flung outward by gravitational tugs of war with Jupiter or Saturn. Then there's the more exotic idea that it's not a planet at all but a primordial black hole, no larger than a grapefruit yet packing the mass of several Earths. That would explain why we can't see it, though detecting its faint gravitational ripples would require entirely new instruments. The challenge now is pinning it down. Telescopes like the Vera C. Rubin Observatory, set to begin sweeping the skies in the coming years, might finally spot its faint infrared glow. Or perhaps we'll infer its location by tracking more of those wayward icy bodies, their paths acting like breadcrumbs leading to the solar system's last great secret. One thing's certain, if Planet 9 exists, it's not just another world, it's a ghostly reminder of how much we still don't know about our own cosmic backyard. Deep in the constellation of Cassiopeia, a cosmic oddball is giving astronomers sleepless nights. It's a pulsar, a type of rapidly spinning neutron star, but this one breaks all the rules. Dubbed Pulsar J0250 plus 5854, it completes a single rotation every 23.5 seconds, making it the slowest spinning pulsar ever detected. And that's the problem. According to everything we know about how these celestial lighthouses work, it shouldn't exist at all. Pulsars are the stellar corpses of massive stars that went supernova, collapsing into spheres so dense a teaspoon of their material would weigh 1 billion tons. What makes them pulse is their mind-bending speed. Some spin hundreds of times per second, sweeping beams of radiation across space like a cosmic strobe light. That's why finding one this sluggish is like stumbling upon a grandfather clock whose hands take days to tick. The prevailing theory says pulsars slow down as they age, losing energy over millions of years until they fade into silence. But this one defies the timeline. At its current spin rate, it should have stopped pulsing eons ago, yet its radio signals remain crisp and clear. So what's keeping it alive? One possibility is that it's feeding off surrounding material, stealing gas from a companion star to power its magnetic field like a cosmic vampire. But here's the twist: no companion has been found. Another idea is that it was born unusually slow, a runt of the neutron star litter with weaker magnetic brakes. There's even speculation it could be an entirely new class of object, a magnetar in disguise, hiding ultra-strong magnetic fields beneath its lethargic surface. The implications are profound. If pulsars can defy their predicted lifespans this dramatically, it means our models of stellar evolution are missing critical pieces. This cosmic zombie shouldn't be pulsing, yet its heartbeat persists, a reminder that the universe loves to throw curveballs. Right now, as you listen, this slow-spinning rebel continues its lazy dance, challenging textbooks and daring us to rethink the life cycles of the dead stars that light up the cosmos. Somewhere in the darkness between constellations Centaurus and Hydra, an invisible force is reeling in our galaxy like a fish caught on a cosmic hook. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it's pulling the Milky Way and hundreds of thousands of neighboring galaxies toward it at over 1 million miles per hour. But here's the catch: we can't see what's doing the pulling. The culprit lies hidden behind the dense star fields of our own galaxy's disk, obscured by a thick curtain of dust and gas known as the zone of avoidance. For decades, this region was astronomy's blind spot, a frustrating void in our maps of the cosmos. Then came infrared and X-ray telescopes, piercing the cosmic fog to reveal the truth. The Great Attractor isn't just a single mystery object, it's the heart of an enormous supercluster called Laniakea, Hawaiian for immeasurable heaven. This sprawling web of galaxies stretches over 500 million light-years, with the Great Attractor acting as its gravitational anchor. Imagine a continental divide for galaxies, where all local flows of stars and gas converge like rivers emptying into an ocean. Our Milky Way, just one droplet in this vast celestial watershed. Yet even Laniakea might not be the whole story. Recent observations suggest something even larger lurks beyond it: the Shapley supercluster, a behemoth 8 times more massive, tugging on the Great Attractor itself. This raises a spine-tingling possibility. What we once thought was the ultimate destination might just be a waypoint in a far grander journey. Some calculations hint that these combined pulls still don't fully account for our galaxy's motion, leaving room for even more enormous structures or something entirely unforeseen lurking in the darkness. The Great Attractor forces us to confront a humbling reality. We're like ants trying to map a forest by studying the dirt at our feet. From our vantage point, swamped by the Milky Way's glow, we're only glimpsing fragments of the cosmic machinery at work. Every breakthrough pulls back another layer, revealing not just answers, but deeper questions about what else might be hiding in the unseen reaches of the universe, pulling us, and everything we know, toward mysteries we've yet to imagine. In the constellation Sagittarius, a cosmic horror story is playing out in real time. A murderous pulsar known as Pulsar B 1957+20, nicknamed the Black Widow, is slowly dissolving its companion star with blistering radiation. This isn't just a celestial oddity, it's a lethal tango between two stars where one partner is being methodically torn apart by the other's deadly embrace. The Black Widow pulsar spins over 600 times per second, whipping beams of high-energy particles and radiation outward like a cosmic blender. Every second, it bombards its neighboring star, a brown dwarf roughly 20 times the mass of Jupiter, with enough energy to strip away its atmosphere atom by atom. What makes this system so chilling is the scale of destruction. The pulsar's radiation pressure has already blasted away nearly 90% of the brown dwarf's mass, leaving behind a smoldering core shrouded in a vast cloud of ionized gas. This evaporating stellar corpse orbits just 2 million miles from the pulsar, closer than some of Jupiter's moons are to their planet, completing a full revolution every 9 hours. That proximity seals its fate. The star's gas is being ripped away so violently it forms a glowing tail stretching over 1 million miles behind it, like a celestial comet caught in a hurricane. But here's where it gets stranger. The The stolen material doesn't just vanish, it feeds the pulsar, swirling into an accretion disk that sporadically ignites with X-ray flares. This creates a feedback loop of destruction. The more the pulsar consumes, the stronger its radiation becomes, which in turn strips even more material from its victim. It's the ultimate cosmic catch-22, a self-sustaining cycle of stellar cannibalism that will eventually leave nothing but a dead core and a bloated, spinning murderer. Astronomers believe systems like this might hold clues to one of the universe's great mysteries, the missing pulsar problem. Theory predicts there should be far more millisecond pulsars, the ultra-fast, older siblings of the Black Widow, than we've observed. The leading explanation: many of them have already finished devouring their companions, leaving no trace of their crimes. If true, the Black Widow offers a rare, grotesque snapshot of this process in action, a fleeting stage in a pulsar's evolution where its lethal appetite is still visible. Yet this isn't just about stellar destruction. The Black Widow's extreme environment acts as a natural physics lab, warping space-time so severely that it subtly alters the pulsar's signals. By studying these distortions, scientists can test Einstein's theory of general relativity in ways no earthbound experiment could replicate. Even in death, the system contributes to our understanding of the universe, a reminder that cosmic violence and scientific discovery often go hand in hand. Right now, as you watch this, that doomed brown dwarf continues its death spiral, its atoms joining the pulsar's deadly glow, one more casualty in a universe where even stars aren't safe from each other. Hanging in the void like a celestial stained glass window, the Red Rectangle Nebula defies every expectation of how dying stars should behave. Located about 2,300 light-years away in Monoceros, this baffling structure isn't just a cosmic accident, it's a near-perfect geometric masterpiece, its glowing red beams forming an almost exact X shape around a central star. Most planetary nebulae billow outward in chaotic, organic clouds, the remnants of a star's death throes, but the red rectangle, it looks as if an unseen architect drafted its lines with a cosmic ruler. The central culprit is a binary star system, HD 44179, where one star has already exhausted its nuclear fuel and begun shedding its outer layers. Normally, this would create a spherical shell of gas, but the presence of a second star, locked in a tight orbital dance, warps the outflow into two opposing cones. These cones intersect at our line of sight, creating that uncanny X pattern. Think of it like twin fire hoses spraying water in opposite directions while spinning. The overlapping streams would form a cross-shaped splash. Yet the geometry is only half the mystery. The nebula's deep red glow, which gives it its name, comes from an unexpected source: fluorescent hydrocarbon molecules, complex carbon-based compounds typically found in interstellar space, not around dying stars. These molecules, bombarded by ultraviolet light from the central stars, re-emit energy as that eerie crimson hue. It's as if the system is harboring the ingredients for organic chemistry in its death throes, a tantalizing hint that the building blocks of life might form in the unlikeliest of places. Even stranger, the red rectangle isn't alone. Hubble has since spotted other biprotic nebulae with similar geometric precision, suggesting this isn't a fluke but a rare yet natural phase of stellar evolution. Some researchers propose these structures could seed the cosmos with complex organic molecules, scattering carbon-rich dust into space like cosmic compost. Others wonder if the red rectangle's symmetry hints at undiscovered physics governing how binary stars interact at the atomic level. What makes this nebula so unsettling is its fleeting nature. In another few thousand years, a blink in cosmic time, its delicate structure will dissipate, leaving only a cooling white dwarf behind. We're catching it in a single frame of an epic film, a transient artwork that will vanish before we fully understand it. Right now, as you watch this, those crimson beams continue their precise, silent expansion, a reminder that even in death, the universe reserves the right to surprise us with beauty we can't yet explain. On the evening of August 15, 1977, a radio telescope in Ohio picked up a signal so startling that the astronomer reviewing the data circled it on the printout and scrawled, "Wow." In the margin, a name that would stick to this day. What made this 72-second burst of radio waves extraordinary wasn't its strength or duration, but its frequency, 1,420 megahertz, a silent slice of the spectrum where cosmic noise is virtually non-existent. It matched exactly the predicted signature of an artificial transmission from deep space. The WOW signal came from the direction of the constellation Sagittarius, near a star group called Chi Sagittarii, with an intensity that spiked 30 times louder than the background static. Most natural cosmic radio sources like pulsars or quasars emit across a range of frequencies, but this was a narrowband signal, the kind you'd expect from a focused transmitter. Even more intriguing, it displayed a subtle frequency drift, as if the source were moving relative to Earth, just like a planet orbiting a distant star would. Then, after those 72 seconds, it vanished, never to repeat despite decades of follow-up searches. Theories about its origin range from the mundane to the extraordinary. Could it have been a reflected Earth-based signal bouncing off space debris? Unlikely. No known satellites or space junk matched its profile, a passing comet's hydrogen cloud. Two were in the area, but their emissions wouldn't explain the signal's precision. Then there's the possibility that doesn't get mentioned in polite scientific circles, an intentional beacon. If so, it would imply a civilization advanced enough to blast a targeted radio burst across hundreds of light years, only to go silent immediately after. What makes the WOW signal so haunting is its isolation. In the 40-plus years since, nothing like it has ever been detected again. SETI Allen Telescope Array and other projects have scanned the same patch of sky thousands of times, hunting for a repeat. The silence speaks volumes. Either we caught a one in a trillion natural fluke, or we intercepted a message never meant for us, like overhearing a single word from a conversation in a crowded room. The mystery endures because it sits at the edge of what science can explain. It's not just about a signal, it's about the uncomfortable truth that the universe might be shouting at us in ways we're only beginning to recognize. Right now, as you watch this, that 72-second blip from 1977 still echoes in the data, a cosmic whisper that refuses to be forgotten. Right now, an invisible storm is raging through our solar system, a torrent of dark matter particles streaming toward Earth at nearly 500,000 miles per hour. Astronomers call it the S1 stream, a relic of a dwarf galaxy our Milky Way cannibalized billions of years ago, now reduced to a river of stars and potentially a hurricane of the universe's most mysterious substance. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it utterly invisible to telescopes. Yet its gravitational pull holds galaxies together, accounting for roughly 85% of all matter in the cosmos. This cosmic hurricane might finally give us a way to touch the untouchable. What makes S1 so special is its trajectory. While most dark matter is thought to move randomly through space, this stream arrives like a fire hose, its particles all traveling in the same direction directly through our corner of the galaxy. That concentrated flow could amplify our chances of detection. Imagine trying to spot a single snowflake in a blizzard versus catching dozens flung at you simultaneously. Current experiments like XENO-NNT and LUX-Zeppelin, ultra-sensitive detectors buried deep underground to shield from cosmic noise, are poised to catch these phantom particles as they breeze through Earth. Their strategy: wait for the rare moment a dark matter particle bumps into an atomic nucleus, creating a minuscule flash of light or heat. But here's where it gets wild. Some theories suggest dark matter might interact with itself through an unknown dark force, meaning S1's particles could collide and annihilate, releasing gamma rays we might spot with telescopes. Others propose actions hypothetical particles so lightweight they behave more like waves, which could transform into photons in strong magnetic fields. Laboratories like CERN CAST experiment are hunting these ghostly ripples right now. Even if we don't detect anything, S1 offers a cruel irony. We're swimming in an ocean of dark matter every second, yet it slips through our hands like smoke. The stakes couldn't be higher. If dark matter interacts with normal matter even faintly beyond gravity, S1 could reveal it. If not, we might need to rewrite physics itself. Either way, this invisible hurricane isn't just a scientific curiosity, it's a cosmic invitation, challenging us to uncover the secrets of the universe's hidden architecture. And right now, as you watch this, countless particles from that ancient, shattered galaxy are passing through your body, silent and unnoticed, carrying clues to the greatest puzzle in modern science. In the cosmic graveyard where dead stars are supposed to stay dead, one stellar corpse just won't take its final bow. Astronomers call it the zombie star, a white dwarf that somehow survived one of the universe's most violent events, a thermonuclear supernova, only to keep shining against all odds. This isn't just a fluke, it's a direct challenge to everything we thought we knew about how stars die. White dwarfs are the dense, Earth-sized cores of sun-like stars that have burned through their fuel. Normally, their fate is sealed, either fade quietly into cold darkness or, if they steal enough mass from a companion star, explode in a Type 1, a supernova, a detonation so predictable it's used as a standard candle to measure cosmic distances. But in 2012, the supernova known as SN 2012Z erupted in the galaxy NGC 1307, and something unprecedented happened. When the smoke cleared, the white dwarf was still there, battered but intact, like a boxer walking away from a nuclear blast. How did it cheat death? The leading theory suggests this zombie star was mid-theft when disaster struck. White dwarfs often siphon gas from neighboring stars, building up a layer of hydrogen until it ignites in a runaway thermonuclear reaction. In SN 2012Z's case, the explosion might have been failed, powerful enough to blast the stolen material into space, but too weak to fully obliterate the dwarf. Think of it like a firework that fizzles after the fuse burns. The outer layers detonated, but the core lived on. But here's where it gets stranger. Follow-up observations revealed the zombie star wasn't just surviving, it was thriving. Brighter and hotter than before the explosion, it seemed rejuvenated, as if the supernova had ripped away its outer shell to expose a fresh, younger-looking surface underneath. Some researchers speculate this could mean white dwarfs have more complex life cycles than we realized, with multiple near-death eruptions before their final demise. Others wonder if we've misclassified supernova altogether, missing a whole category of partial explosions that leave stars wounded but alive. The implications ripple far beyond one stubborn star. If white dwarfs can endure supernova, it means these cosmic yardsticks we've used to measure the universe's expansion might not be as uniform as we thought. Distant galaxies could be closer or farther than we've calculated, skewing our models of dark energy and the fate of the cosmos. Even more tantalizing. This zombie star's survival hints that some white dwarfs might undergo repeated explosions over millennia, potentially explaining weird stellar remnants that have puzzled astronomers for decades. Right now, as you watch this, that undead star still glows in the aftermath of its brush with annihilation, a cosmic rebel that refuses to play by the rules. It's a reminder that the universe loves a good plot twist, and when it comes to stellar death, even the textbooks might need rewriting. Of all the cosmic mysteries we've uncovered, few have burned as brightly in the public imagination as Tabby's star, a seemingly ordinary sun called KIC 8462852, located 1,400 light-years away in Cygnus. At first glance, it's just another yellow-white dwarf, unremarkable among the billions in our galaxy. But its light tells a different story, a tale of erratic, dramatic dimming so bizarre it sparked headlines about alien megastructures and cosmic puzzles we still can't fully explain. The star first grabbed attention in 2015 when citizen scientists combing through Kepler Space Telescope data noticed its light dropping by up to 22% at irregular intervals, far more than any planet could block. These weren't the tidy, periodic dips of an orbiting world. They were erratic, asymmetrical plunges, like someone flickering a cosmic light switch at random. Some dips lasted days, others weeks, with no predictable pattern. Even stranger, the star's overall brightness has been slowly fading for over a century, as archival photographic plates revealed. Whatever's happening here, it's not just a fleeting anomaly, it's a century-spanning enigma. Cue the speculation, the most electrifying theory, a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harness a star's energy, possibly made of orbiting solar collectors that intermittently block its light. While compelling, this idea faced a harsh reality check. Subsequent studies found the dimming affects different wavelengths unevenly, which cosmic dust, not solid structures, would explain. Yet even dust doesn't quite fit. Normal interstellar dust scatters blue light more than red, but Tabby's star dims all wavelengths almost equally, suggesting the particles are either absurdly fine or arranged in ways dust shouldn't behave. Then came another twist. In 2017, the star's light suddenly dipped again, and astronomers worldwide trained telescopes on it like a cosmic crime scene. What they found deepened the mystery. The dimming wasn't uniform. Some colors of light faded more than others, hinting at a bizarre dust cloud that's both clumpy and translucent. One team proposed a shattered exomoon's debris could create such a cloud, a ring of planetary rubble spiraling into the star. Others suggest swarms of comets or even a warped protoplanetary disk, though none perfectly match the data. What makes Tabby's star so captivating isn't just the puzzle itself, but what it represents, a reminder of how much we don't know. Every time we think we've nailed down an explanation, the star throws another curveball. It's become a laboratory for extreme astrophysics, testing our ability to distinguish between natural phenomena and just maybe something beyond nature. Whether it's dust, debris, or something we haven't imagined yet, one thing's certain: the universe loves to keep us guessing. And right now, as you watch this, that 1400-year-old light still flickers toward us, carrying secrets from a star that refuses to be understood. Buried under a mile of Antarctic ice, a high-tech observatory called IceCube is playing cosmic detective, catching ghostly particles that have traveled billions of light years to reach us. These aren't just any particles, they're neutrinos, the universe's most elusive messengers, so insubstantial they can pass through entire planets like they're not even there. Yet some of these phantoms pack an unbelievable punch, carrying energies 1,000 times greater than anything our most powerful particle colliders can produce. And here's the kicker: we have no idea what cosmic accelerators are launching them at us from beyond our galaxy. Neutrinos are nature's stealth fighters, nearly massless, electrically neutral, and barely interacting with matter. Trillions pass through your body every second, leaving no trace. But the ultra-high-energy neutrinos IceCube detects are different. They're the universe's extreme athletes, racing across intergalactic space with energies measured in petaelectron volts, equivalent to a baseball moving at 100 miles per hour squeezed into a single particle. When one of these rarities finally hits an atomic nucleus in the ice, it creates a faint blue flash called Cherenkov radiation, a cosmic fingerprint that reveals its origin. The mystery: most of these intergalactic trespassers point back to empty patches of sky with no obvious source visible. Unlike light or radio waves, neutrinos don't bend or scatter, meaning their path should lead straight back to their violent births. Yet time and again, astronomers trace them to cosmic voids, as if the universe has invisible particle cannons hidden in the darkness. The leading suspects are active galactic nuclei, supermassive black holes devouring matter with such fury they launch jets of plasma near light speed, or perhaps tidal disruption events where stars ripped apart by black holes become natural particle accelerators. There's even speculation about more exotic origins, decaying dark matter, cosmic strings, or collisions of primordial antimatter. What makes these ghost particles so invaluable is their defiance. While light gets absorbed or deflected by cosmic dust and magnetic fields, neutrinos travel unimpeded, delivering pristine information from the universe's most chaotic environments. When IceCube detected a neutrino from Blazar TXS 0506 plus 056 in 2017, the first identified extragalactic source, it opened a new window on high-energy astrophysics. Suddenly, we could correlate neutrino data with gamma-ray and optical observations, piecing together how black holes engineer these unimaginable particle bursts. Yet for every answer, there are a dozen new puzzles. Why do some neutrino hotspots correspond with gamma-ray quiet regions? How can a single source produce neutrinos across such a vast energy range? And most perplexing of all, what cosmic phenomena remain hidden, their neutrino signatures reaching us without any accompanying light. Every detection is like intercepting a bullet from a sniper we can't see, each one carrying clues about the invisible warfare raging in deep space. Right now, as you watch this, these ghostly projectiles are piercing Earth by the thousands, their origins still cloaked in mystery. They remind us that the universe doesn't just communicate in light and sound, it whispers in particles we're only beginning to decode, each one a postcard from the most violent corners of existence. Out in the cosmic wilderness, untethered from any star, a legion of rogue planets drifts through the eternal night, worlds without sunrises, exiled from the systems that birthed them. Astronomers estimate there could be billions of these nomadic planets in our galaxy alone, outnumbering stars by as much as 20 to 1. Some were violently ejected during the gravitational chaos of their solar system's youth, flung into the void by planetary pinball. Others may have formed alone in the cold collapse of interstellar gas clouds, never knowing the warmth of a parent star. But here's the twist: these dark wanderers might not be the frozen wastelands we once assumed. Take CFBD Sir 2149, for example, a rogue planet just 100 light-years away with temperatures hot enough to boil water. Without a star to keep it warm, how does it retain such heat? The answer lies in its youth. This planetary fugitive is a mere 50 to 120 million years old, still glowing from the energy of its formation. Infrared telescopes have detected methane and water vapor in its atmosphere, hinting at complex chemistry unfolding in the darkness. But the real stunners are the stealth ocean theory's rogue planets with thick hydrogen atmospheres trapping geothermal heat, possibly maintaining subsurface oceans liquid for billions of years. Enceladus and Europa have shown us that life doesn't need sunlight, just liquid water and energy. A rogue planet with volcanic vents under an ice shell could harbor the same potential, hidden beneath miles of frozen crust. Then there's the mind-bending prospect of rogue Earth's rocky planets like our own, exiled into the cold. Simulations suggest these worlds could retain dense atmospheres if they're massive enough, with pressure keeping water liquid even in the absence of stellar warmth. Some might even have temporary suns, internal heat sources like radioactive decay or tidal flexing from orbiting moons creating geothermal hotspots. Imagine a planet where the only light comes from bioluminescent lifeforms in pitch-black seas, or auroras crackling above icy plains stirred by a powerful magnetic field. Detecting these cosmic outcasts is a fiendish challenge. Without starlight to illuminate them, they're nearly invisible until one passes in front of a distant star, its gravity bending the light like a lens in a phenomenon called microlensing. That's how we've spotted most of them, fleeting distortions in starlight lasting mere hours. but future telescopes like NAS and Nancy Grace Roman Space Telescope could revolutionize the hunt, potentially discovering thousands more. What makes rogue planets so haunting is their defiance of cosmic norms. They prove that planets don't need stars to exist, and by extension, neither might life. If life can emerge in these sunless realms, it would mean the galaxy is teeming with habitats we've barely considered, drifting unseen in the black. Right now, as you watch this, countless rogue worlds are sailing through the interstellar deep, carrying the possibility that the universe's greatest secrets, and perhaps even its neighbors, might be hiding in the darkest corners of all. Hidden in the depths of the constellation Hercules, a cosmic anomaly glows with an eerie blue halo, the only one of its kind ever observed. The Blue Ring Nebula isn't just a celestial oddity. It's a stellar crime scene, the aftermath of a violent merger between two stars that defies every classification in the astronomy playbook. Discovered in 2004 and studied for over 16 years, this structure remains unmatched. A perfect, symmetrical ring of blue gas encircling a central star with no known counterpart in the observable universe. What makes this nebula so baffling is its unprecedented anatomy. Most planetary nebulae form when dying stars shed their outer layers, creating intricate, uneven shells of glowing gas. The Blue Ring Nebula, its ultraviolet glow comes from a double shock wave, one expanding outward, the other rebounding inward, sculpted by the cataclysmic collision of two stars into one. Imagine two molten spheres of metal slamming together in space, their merged core still throbbing from the impact while a tsunami of superheated gas races outward at nearly 200,000 miles per hour. That's the cosmic violence behind this ethereal ring, but the real mystery lies in what we can't see. Spectroscopic observations reveal the central star is cloaked in a thick disk of dust, blocking our view of its surface. That disk is the smoking gun debris from the stellar merger, a swirling graveyard of vaporized star stuff. Normally, merged stars settle down within millennia, but this one's still shedding material like a celestial tornado, its turbulent winds ionizing the surrounding gas into that haunting blue hue. The most tantalizing clue, the nebula's lack of hydrogen. Most stars are hydrogen furnaces, yet the Blue Ring's gas is rich in helium and other heavy elements, suggesting the merger tore apart stars already in advanced stages of evolution. One theory proposes a sun-like star devoured a smaller white dwarf companion, triggering a thermonuclear firestorm that blasted away both stars' outer layers. Another suggests two white dwarfs collided, narrowly avoiding a supernova but leaving behind this glowing wreckage. Yet none of this fully explains the ring's symmetry. Shock waves from mergers usually produce chaotic, clumpy structures, not perfect geometric halos. Some researchers speculate magnetic fields, twisted during the collision, could have funneled the ejected material into this precise formation. Others wonder if we're witnessing a fleeting phase of stellar evolution, a cosmic metamorphosis caught mid-transformation. What's certain is that the Blue Ring Nebula is a Rosetta Stone for understanding extreme stellar relationships. Its existence hints that binary star mergers might be far more common and far stranger than we ever imagined. Right now, as you watch this, that blue halo continues to expand, carrying secrets of a celestial tantrum that could rewrite how we think stars live, die, and sometimes consume each other. Deep in the constellation Sagittarius, a cosmic time bomb lurks, a star so magnetically vicious it could erase Earth's entire digital infrastructure from 50,000 light-years away. Meet SGR 01804.0, a magnetar whose magnetic field is 1,000 trillion times stronger than Earth's, warping the very fabric of space-time around it. This isn't just a neutron star. It's a magnetic monster capable of unleashing eruptions so violent they briefly outshine every star in the Milky Way combined. What makes magnetars so terrifying is how they weaponize magnetism. When one of these stars undergoes a starquake, its crust cracking under magnetic pressures so extreme they rival black holes, it releases gamma-ray flares in milliseconds. The energy, equivalent to the sun burning for 100,000 years. In 2004, a flare from SGR 1806-20 actually ionized Earth's upper atmosphere from halfway across the galaxy, despite being harmless to life. Had it occurred within 10 light years, it might have triggered a mass extinction by stripping our ozone layer. Yet the real magic and horror lies in how these fields distort reality. A magnetar's magnetism is so intense it twists the vacuum of space itself, a phenomenon called vacuum birefringence. Light passing near it splits into two polarized beams as if space becomes a cosmic prism. Even atoms stretch into needle-thin shapes in its presence, with electrons forced into bizarre helical orbits. If you ventured within 1,000 kilometers of one, your body's atoms would be torn apart by magnetic forces before gravity even had a chance to crush you. Then there's the ultimate enigma. Magnetars shouldn't exist this long. Based on their energy output, their magnetic field should decay within 10,000 years. Yet we've found dozens, some appearing billions of years old. One theory suggests their cores harbor exotic quantum fluids that regenerate the field like a cosmic perpetual motion machine. Another posits they're not neutron stars at all, but quark stars, a hypothetical state of matter so dense protons and neutrons dissolve into their component particles. What makes these magnetic beasts so valuable to science is their role as extreme physics labs. By studying their flares, we've glimpsed hints of quantum gravity, the elusive bridge between Einstein's relativity and quantum mechanics. Their bursts also serve as cosmic lighthouses, their polarized signals carrying clues about interstellar space's structure. Yet for all their ferocity, magnetars are fleeting. Within another few millennia, SGR 01804.0's field will fade, leaving behind a cold, dead husk. Until then, it remains one of the universe's most beautifully destructive phenomena, a reminder that even in stillness, the cosmos thrums with unimaginable power. The silence of the cosmos is deafening. With billions of potentially habitable planets in our galaxy alone, why haven't we found a single whisper of another civilization? This eerie absence forms the heart of the Fermi paradox, the glaring contradiction between the high probability of alien life and our total lack of evidence for it. One chilling explanation: the Great Filter, a hypothetical cosmic bottleneck that silently eliminates intelligent life before it can spread beyond its home world. Whether it's lurking in our past or waiting in our future, this filter could be the reason the universe feels so empty. The Great Filter isn't a single event but a spectrum of existential threats, catastrophes so universal they cull civilizations like a cosmic grim reaper. Some filters might be behind us, hurdles Earth barely survived. The jump from single-celled to multicellular life took nearly 2 billion years, a leap so rare it might explain why we've found no alien microbes. Others could lie ahead, a deadly phase all technological civilizations hit, like self-annihilation through nuclear war, runaway artificial intelligence, or ecological collapse. The terrifying implication: if the filter is ahead of us, humanity's window of existence might be far narrower than we've dared to imagine. But the filter might not be biological or technological at all. Cosmic threats like gamma-ray bursts, stellar explosions that sterilize entire galaxies in seconds, could reset the clock on life periodically. Or perhaps the universe is littered with the ruins of civilizations that cracked interstellar travel only to awaken something worse in the dark: predatory AI, berserk nanotechnology, or even dormant alien weapons lurking in the void. Some theories suggest advanced societies inevitably discover universe-ending physics experiments and voluntarily halt their expansion to avoid catastrophe. The scariest version of the Great Filter: we're alone because we're first. If life needs rare elements forged in multiple generations of stars, Earth might be among the earliest planets capable of hosting complex life. In this scenario, trillions of civilizations could blossom in the future, but for now, the cosmos is still warming up, and we're the outliers peering into an empty nursery. Yet there's a glimmer of hope. If the filter is behind us, if beating those astronomical odds means we've already survived the universe's deadliest gauntlet, humanity could be poised to become the ancient, spacefaring civilization future species wonder about. Either way, the Great Filter forces us to confront a haunting truth. The cosmos isn't just indifferent to life. It might be actively hostile to it, and every silent radio telescope only deepens the mystery. At this very moment, an invisible force is stretching the universe apart at an ever-increasing rate. A phenomenon so baffling we've labeled it with the ultimate scientific shrug: dark energy. Think of it as cosmic anti-gravity, an ethereal pressure woven into the fabric of space itself, pushing galaxies away from each other faster than gravity can pull them together. What makes dark energy so unsettling isn't just its dominance. It accounts for 68% of the universe's total energy, but the fact that we have no idea what it actually is. The discovery came in the late 1990s when two teams studying distant supernova made the same chilling observation. These exploding stars were dimmer than expected, meaning the space between us and them had stretched more than anyone predicted. The universe wasn't just expanding, it was accelerating, as if some hidden hand had pressed the cosmic gas pedal. Here's the kicker: Einstein's equations actually allowed for this possibility. His cosmological constant, originally introduced to keep the universe static, a notion he later called his greatest blunder, turned out to describe dark energy perfectly, except no one knows what's causing it. Leading theories range from the mind-bending to the metaphysical. One idea suggests dark energy is the intrinsic energy of empty space itself, quantum fields flickering in the vacuum, generating repulsive force. The problem: calculations predict this vacuum energy should be 120 orders of magnitude stronger than what we observe, a discrepancy so colossal it's been called the worst theoretical prediction in physics history. Another hypothesis invokes an exotic fluid called quintessence, a dynamic field that permeates space and changes over time. Then there's the radical notion that dark energy isn't real at all, that our measurements are skewed because we're in a vast, underdense region of the universe, a cosmic bubble distorting our view. The implications are staggering. If dark energy's strength increases over time, it could trigger the Big Rip, a scenario where not just galaxies but atoms themselves are torn apart in the universe's final milliseconds. Alternatively, if it weakens, gravity might regain control, collapsing the cosmos in a big crunch. The most likely outcome: a slow, icy fade as galaxies vanish beyond our cosmic horizon, leaving future civilizations with a sky nearly empty of stars, a lonely, dark eternity. Yet dark energy might hold an even deeper secret. Some theorists speculate it's linked to the nature of consciousness or the multiverse, a shadow of other universes pressing against ours. Others wonder if it's evidence we've completely misunderstood gravity, requiring a rewrite of Einstein's relativity. Every new galaxy survey, every map of the cosmic microwave background brings us closer to answers, or perhaps to questions we haven't even thought to ask. Right now, as you watch this, dark energy is silently reshaping the fate of everything, its mystery as vast as the void it's creating. In October 2017, astronomers spotted something streaking through our solar system that shattered all expectations. A reddish, cigar-shaped object moving so fast it could only have come from another star. They named it Oumuamua, Hawaiian for scout, but this interstellar visitor was no ordinary space rock. From the moment it was detected, Oumuamua defied classification, behaving in ways that left scientists scrambling for explanations, and even flirting with the possibility it might not be natural at all. Initially, its elongated shape alone was bizarre. Most asteroids and comets are lumpy or roughly spherical, but Oumuamua stretched over 800 meters long while being just 80 meters wide, a cosmic toothpick tumbling through space. Then came the real shock. As it slung past the sun, it accelerated slightly as if pushed by an unseen force. Comets often speed up when their ices vaporize in sunlight, creating a visible tail of gas and dust. But Oumuamua showed no outgassing, no tail, no coma, nothing to explain its unexpected boost. Theories exploded like supernova. Could it be a hydrogen iceberg, its invisible gas jets nudging it forward? Maybe an ultra-porous dust bunny of fragile cosmic debris, light enough for solar radiation to push it. Then came the wilder ideas, a fragment ripped from a Pluto-like world, its nitrogen ice sublimating stealthily, or even an artificial solar sail, a piece of alien technology coasting on starlight. The lack of a visible tail didn't help. If it was outgassing, why no dust? Unless, some speculated, the debris was trapped beneath an unusual surface crust, venting through narrow fissures we couldn't detect. Then there's the spin. Oumuamua didn't rotate smoothly like most asteroids. It tumbled chaotically, as if it had survived a violent collision or been subjected to forces we don't fully understand. Add to that its extreme reflectivity, at least 10 times shinier than typical comets, and you've got an object that feels engineered by a cosmic trickster. The real frustration, we only had weeks to study it before it vanished beyond the reach of our telescopes, leaving behind a trail of data too sparse for definitive answers. Was it a comet with exotic chemistry, an asteroid sculpted by unknown processes, or something even stranger? The truth is, Oumuamua's greatest legacy might be the door it kicked open. Proof that interstellar visitors are real, and the next one could hold the answers we're still missing. Until then, it remains a gleaming enigma, a cosmic riddle wrapped in a mystery, hurtling silently through the void. Right now, just 2.5 million light-years away, a cosmic horror story is unfolding, one that will eventually pull our galaxy into its grasp. The Andromeda Galaxy, that faint smudge of light in our night sky, isn't just our nearest galactic neighbor. It's a predator, a celestial cannibal silently devouring smaller galaxies in a feeding frenzy that's been raging for billions of years. And what makes this truly terrifying? We're next on the menu. Hubble's sharp eye has caught Andromeda red-handed, its gravitational claws shredding dwarf galaxies like M32 and M110, leaving behind streams of stars, ghostly remnants of its meals. These aren't clean mergers, they're violent feasts. Stars ripped from their orbits form vast, looping rivers around Andromeda's disk, while clusters of orphaned suns drift like cosmic debris. One particularly gruesome snack, the Triangulum Galaxy, is already being stretched into a stellar noodle, its stars smeared across space in a process astronomers call spaghettification. But here's the twist: Andromeda isn't just a mindless destroyer. Its cannibalism is sculpting its future. Every galaxy it consumes adds to its mass, tightening its gravitational grip on the Milky Way. Simulations show that in about 4.5 billion years, the two galaxies will slam together in a titanic collision, a slow-motion crash that will warp both spirals into a new, elliptical galaxy dubbed Milkdromeda. The dance has already begun. Right now, Andromeda barrels toward us at 250,000 miles per hour, a fate written in the stars themselves. What's chilling is how ordinary this apocalypse is. Galactic cannibalism isn't some rare cosmic fluke, it's the rule. The universe runs on a brutal food chain where big galaxies eat small ones, growing fatter until they too are consumed. Even our Milky Way is a predator, currently digesting the Sagittarius dwarf galaxy. But Andromeda, it's the apex predator of our local group, and its hunger is insatiable. Yet there's strange beauty in this destruction. When galaxies collide, they rarely smash stars together. Space is too vast. Instead, their gravity tangles like invisible hands, weaving new structures from the wreckage. The collision will fling our solar system to the galaxy's outskirts, bathing us in a sky where Andromeda's spiral fills half the heavens before fading into a shapeless glow. Life, if it still exists, will gaze up at a universe remade. So while Andromeda's feasting seems distant, it's a reminder the cosmos doesn't stand still. Galaxies rise, fall, and merge in an endless cycle, and we're just brief witnesses to one act in the grand play. The Milky Way's fate is sealed. All that's left is to watch and wonder what strange new universe will emerge from the wreckage. Imagine if the universe had a hidden self-destruct button, one that could be pressed at any moment, erasing reality itself without warning. This isn't science fiction. It's a terrifying possibility rooted in quantum physics called vacuum decay. Here's the nightmare scenario. Our universe might not be in its true, most stable state. Instead, it could be trapped in a false vacuum, like a marble resting precariously on a hillside. And if that marble rolls, if even the tiniest patch of space tips into the lower energy, true vacuum, it could trigger an unstoppable chain reaction that rewrites the laws of physics at the speed of light, wiping out everything in existence. The math behind this doomsday is as elegant as it is horrifying. Quantum fields dictate how particles behave, and their energies shape the fabric of reality. Most of the time, these fields sit in their lowest possible energy states. Think of water settling at the bottom of a bowl. But some theories suggest the Higgs field, the one responsible for giving particles mass, might be in a metastable state, like water trapped on a ledge halfway down a cliff. It's stable until it isn't. If a quantum fluctuation nudges it over the edge, the Higgs field could collapse into a lower energy state, releasing a bubble of true vacuum. Inside that bubble, the laws of physics as we know them cease to exist. Atoms gone, light redefined, even time and space could unravel, the scariest part. It could happen anywhere, a random quantum event in deep space or even in a lab particle collider might spawn this apocalyptic bubble. It would expand at light speed, its boundary a wall of cosmic annihilation. By the time we saw it coming, it would already be too late. 1 millisecond, Earth exists, the next it doesn't. No sound, no flash, just an instantaneous rewrite of reality, leaving no trace that we, or the universe, ever existed. But don't panic yet, the odds are astronomically low. The universe has lasted 13.8 billion years without decaying, suggesting our vacuum might be more stable than we fear. Some physicists argue the Higgs field's current state could last for gagons of years, far longer than the stars will burn. Others counter that black hole collisions or high-energy experiments might accidentally trigger decay, though even the most powerful particle colliders pale compared to the cosmic rays constantly bombarding Earth. Vacuum decay isn't just a physics thought experiment. It forces us to confront the fragility of reality itself. The universe might not be a fixed stage but a house of cards, balanced on quantum laws we barely understand. And right now, as you watch this, that instability hums beneath everything, a silent reminder that existence, for all its grandeur, might hang by the thinnest of threads. At the intersection of quantum physics and science fiction, a bizarre new form of matter pulses without any energy input, a cosmic perpetual motion machine breaking one of nature's most fundamental rules. These are time crystals, structures that oscillate, rotate, or morph in repeating cycles without losing energy, essentially defying the second law of thermodynamics. Imagine a diamond that spins on its axis forever without being pushed, or a snowflake that changes its pattern every few seconds for all eternity. That's the mind-bending reality of time crystals, and they're not just theoretical curiosities anymore. Scientists have actually created them in labs, unlocking a realm of physics where time itself becomes a playground. What makes time crystals so revolutionary is how they cheat the universe's energy economy. Normally, all systems lose energy over time, pendulums slow, springs wear out, even stars exhaust their fuel. but time crystals exist in a strange quantum state where their lowest energy configuration still allows perpetual motion. They don't violate physics so much as exploit a loophole. Instead of reaching equilibrium like ordinary matter, they're forever stuck in a cycle, oscillating between states without ever settling down. Picture a clock that ticks forever without winding, powered not by gears but by the quantum fabric of reality itself. The key to their behavior lies in time's symmetry breaking. Most physical systems look the same whether time runs forward or backward. Drop a ball, and the motion reverses neatly if you flip the timeline. Time crystals shatter this symmetry. Their oscillations lock into a fixed rhythm, creating an arrow of time within the material itself. This isn't just academic, it hints that time might emerge from quantum interactions in ways we've barely begun to grasp. Some researchers speculate time crystals could be the first examples of non-equilibrium matter, a whole new phase of existence as fundamental as solids, liquids, or plasmas. Creating them requires quantum sleight of hand. Early versions were forged in labs using chains of ytterbium atoms chilled near absolute zero and hit with precisely tuned laser pulses. The atoms didn't respond immediately but settled into a rhythmic dance, flipping their spins at a fraction of the laser's frequency, like a drumbeat that somehow lags behind the drummer's sticks. Even stranger, these crystals can exist at room temperature, as shown in experiments with diamond defects, suggesting they might be hiding in plain sight throughout nature. The implications are staggering. Time crystals could revolutionize quantum computing by creating flawlessly synchronized qubits immune to external noise. They might even model exotic physics like black hole dynamics or cosmic strings phenomena where time behaves strangely. And if naturally occurring time crystals exist in neutron stars or other extreme environments, they could be ticking away right now, unnoticed cosmic metronomes keeping time in the void. Yet the deepest mystery remains. Do these crystals hint at a deeper connection between time and quantum mechanics? Some theorists wonder if they're glimpses of a larger truth, that time isn't just a backdrop to the universe but something that emerges from quantum relationships, like temperature arising from atomic motion. If so, time crystals might be the first whispers of a theory that rewrites how we perceive reality itself. For now, they stand as physics' most enchanting paradox, structures that move without moving, clocks that tick without counting down, and perhaps harbingers of a new understanding of time. If black holes are the universe's ultimate one-way streets, where not even light can escape their gravitational grip, then white holes might be their cosmic opposites, theoretical exits where nothing can enter, only erupt. These hypothetical monsters are like reverse black holes, spewing out matter and energy with such force that approaching them would be impossible. Imagine a cosmic fire hydrant blasting reality itself into space, a fountain of existence with no off switch. While no white hole has ever been observed, their potential existence isn't just science fiction, it's a tantalizing solution to some of the universe's most violent mysteries. The math behind white holes emerges straight from Einstein's equations of general relativity. Just as black holes warp space-time into a bottomless pit, white holes appear as mathematical mirror images, regions where space-time funnels outward, ejecting everything inside. Some physicists speculate they could be the other end of a black hole's tunnel, the exit point of an Einstein-Rosen bridge or wormhole. But here's the catch. While black holes form naturally from collapsing stars, white holes would require conditions so extreme they defy known physics. They'd need to erupt from nothingness, violating entropy by reassembling scattered matter and energy into pristine order. Yet the cosmos loves breaking rules. One compelling theory suggests white holes could explain fast radio bursts, those millisecond cosmic screams of energy with no clear source. If a black hole's interior rebounded like a compressed spring, its collapse could reverse into a white hole explosion, channeling trapped energy into a single catastrophic burst. Even more bizarre, some models propose that our own Big Bang might have been a white hole event, the explosive rebirth of a collapsed universe from a previous cosmic cycle. The problem: white holes are infuriatingly elusive. If they exist, they'd likely be short-lived, evaporating instantly or collapsing back into black holes under their own instability. Detecting one would require catching the universe in the act of violating its own laws, a fleeting glimpse of impossibility. Until then, they remain one of physics' most fascinating what-ifs, a reminder that the universe might still hold doors we haven't even imagined knocking on. And somewhere out there, in the silent dark, one might be waiting to prove us right, or blow every equation we've ever written to smithereens. Right now, cosmologists are locked in a silent battle over one of astronomy's most fundamental numbers, the rate at which the universe is expanding. This isn't just some academic debate, it's a full-blown crisis dubbed the Hubble tension, a discrepancy so stubborn it might force us to rewrite the laws of physics. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, whispering an expansion rate of about 67 kilometers per second per megaparsec. On the other, modern measurements of pulsating stars and exploding supernova insist it's closer to 73. That gap might seem small, but in a universe governed by precise equations, it's the equivalent of two clocks ticking at irreconcilable speeds, and no one knows which one's broken. The heart of the problem lies in how we measure cosmic distances. The early universe's expansion rate is etched into the cosmic microwave background, mapped by satellites like Planck with exquisite precision. But when we cross-check that with nearby celestial landmarks, Cepheid variable stars whose rhythmic brightening acts as a cosmic yardstick, or Type 1, a supernova that explode with predictable brilliance, the numbers refuse to align. It's as if the universe accelerated sometime after the Big Bang, leaving behind two conflicting histories. At first, astronomers blamed measurement errors, but after decades of refined data, the gap hasn't budged. If anything, it's grown more glaring. This isn't just about fixing a math error. The Hubble tension hints at something profound missing from our cosmic playbook, an invisible ingredient or a flaw in Einstein's relativity. One tantalizing possibility: early dark energy, a mysterious force that briefly surged during the universe's infancy, tweaking its initial expansion before vanishing without a trace. Alternatively, dark matter might interact with itself in ways we've never detected, or gravity could behave differently on cosmic scales. There's even speculation about parallel universes subtly warping our measurements, their gravity leaking into ours like noise from another room. Yet the most unsettling scenario is that both measurements are right, that the universe's expansion rate genuinely differs depending on where and when you look. If true, it would mean the cosmos isn't as uniform as we've assumed, with hidden cracks in space-time or unevenly distributed dark energy creating cosmic neighborhoods that stretch faster than others. Imagine blowing up a balloon that doesn't inflate evenly, with some patches growing taut while others remain slack, a universe with cosmic wrinkles we've never noticed until now. The stakes couldn't be higher. If the Hubble tension holds, it could upend our understanding of everything from the Big Bang's aftermath to the universe's ultimate fate. New telescopes like the James Webb Space Telescope and next-generation observatories are racing to settle the debate, hunting for overlooked variables or exotic physics hiding in plain sight. Until then, this quiet conflict remains one of science's greatest open questions, a puzzle written in the stars waiting for someone to crack its code. And with every passing second, the universe keeps expanding, indifferent to our confusion, its true speed still just out of reach. Tabby's star isn't the only cosmic oddball making astronomers question everything. Across the galaxy, a growing list of stellar anomalies, stars flickering in ways that defy natural explanation, are raising eyebrows and fueling speculation about extraterrestrial engineering. Take KIC 8462852's distant cousin, EPIC 246393548, a star whose light curves plunge by up to 80% in irregular, jagged drops. Unlike the smooth dimming of a planet transit, these dips look like someone's turning a celestial dimmer switch on and off at random. Then there's VVVWIT07, a giant star 30,000 light-years away that periodically vanishes for months, eclipsed by some vast, unseen companion. These aren't just quirks, they're cosmic glitches screaming for investigation. What makes these stars so compelling is the sheer diversity of their strangeness. Some, like Boyajian's star, show asymmetric dips hinting at swarms of debris or dust clouds. Others, like HD 139139, flicker erratically while emitting bizarre infrared flares, behavior that might fit a star surrounded by a Dyson swarm under construction, its energy collectors intermittently reflecting or absorbing light. The star TYC 7037891-1 behaves even more oddly, dimming predictably every 2 years exactly as if on a cosmic schedule. The most chilling candidate, Piazzi-Bilski's star, a stellar oddity packed with radioactive elements like Einsteinium and plutonium materials that vanish instantly in nature unless actively produced. Could these be signatures of advanced nuclear waste disposal, or even fuel processing on an unimaginable scale? The search for answers has birthed entire new fields of astronomy. Projects like Breakthrough Listen now train radio telescopes on these stars, hunting for artificial signals buried in the noise. Others use machine learning to sift through millions of light curves, flagging anomalies that human eyes might miss. But here's the twist: the more we look, the weirder it gets. Recent studies suggest up to 15% of main sequence stars might show unusual dimming, far too many to all be alien megastructures. Nature, it seems, has a flair for the dramatic, crafting phenomena we've yet to imagine. Yet the tantalizing possibility remains: what if even one of these stars harbors intelligence? The universe is 14 billion years old, plenty of time for civilizations to rise, engineer their suns, and fade into cosmic history. Their artifacts might still orbit, silent and crumbling, waiting for us to recognize them not as natural wonders but as ruins. Every strange light curve is a message in a bottle tossed across the void. Whether the answer is aliens or astrophysics, we've yet to discover. One thing's certain: the stars have more secrets than we ever dreamed. And the hunt for them has only just begun. From rogue planets drifting in eternal darkness to magnetars capable of bending space itself, we've journeyed through 25 cosmic phenomena that defy logic, challenge our understanding, and prove the universe is far stranger than we ever imagined. These aren't just quirks of deep space, they're glaring reminders of how much we don't know. Fast radio bursts scream across billions of light years with no discernible source. Dark matter flows through you right now, untouched and untouchable. White holes, wormholes, and zombie stars blur the line between science and speculation. And lurking behind it all, the chilling silence of the Fermi paradox, asking the question we still can't answer: where is everyone? What ties these mysteries together isn't just their strangeness, it's their humility. Every time we think we've cracked the cosmic code, the universe laughs and throws another paradox our way. The Hubble tension pits the past against the present, vacuum decay threatens reality itself, and the great filter looms over our future like a cosmic guillotine. Yet here's the beautiful truth: these aren't dead ends, they're invitations. Each anomaly is a door waiting to be kicked open, a puzzle begging to be solved. And the next breakthrough could come from anywhere: a lab, a telescope, or even you. So tell us, which of these cosmic enigmas keeps you up at night? Is it the eerie precision of the red rectangle nebula, or the predatory hunger of Andromeda? The whisper of the wow signal, or the silent terror of vacuum decay? Drop your thoughts in the comments. We're as obsessed with these mysteries as you are. And if you're craving more deep dives into the universe's greatest secrets, hit that subscribe button. The cosmos isn't done surprising us yet, and neither are we. Until next time, keep looking up and never stop wondering what's really out there.